Hi guys, my name's Anna. My group and I will be presenting on chapter 3, the process analysis. So in this chapter, we're going to go over how to begin a operation by drawing the process flow diagram and capacity for one-step process. And we're going to see how to compute a float rate, utilization, and the cycle time. And we're going to see how to analyze a multi-step process and locate the bottleneck works. And finally, we're going to see how will the time to produce a certain quantity conclusion. Okay, first off, I want to talk about the process analysis, the title of our chapter. A process analysis is a framework that can be used for everyone who runs a business. It provides a rigorous framework for understanding the detailed operation of a business. It can be used by one who owns these smaller restaurants, and this is the responsibility of the owner. Um, so the responsibility of the owner is to do a process analysis before they operate a business of themselves. And then the purpose of the process analysis is to make the business better. Everyone hopes their business will be great if they operate one, right? And because it opens a black box of the operation and peeks inside by identifying and analyzing all the activities involved in serving one unit of demand, or put differently, but in providing one unit of supply. Okay, moving on to process flow diagram. A process flow diagram, it is a graphical way to describe the process. It helps us to structure the information that we collect as we try to improve our understanding of the process. And the best way to begin any analysis of the operation is by drawing this process flow diagram. So on this side, we have a process flow chart diagram of a Subway restaurant, for example. So this is all the steps that will take by employee to complete the order of the customer. And they're gonna start off asking the number of sandwich that they like, and then they're gonna ask for the preference of bread, the cheese that the customer desires, and then if they wanted to get their toasted sandwich toasted or not, and whether the customer is yes or no, they're gonna go on to asking for the toppings, and then if you provide a list of vegetables or not, they'll ask you for the condiments too, and then you go to towards the counter to the cashier, and then they'll ask you if you want any food or drink or not, and then lastly you'll pay for the item and leaves. This is the process of the Subway restaurant, how it works, and this is what we call the process flow diagram. Example of it. Okay. Next we have what is a resource? So what is a resource is a group of people and or equipment that transforms input into output. For instance, when the customer reaches to the front of the line, she or he will get greeted by the employee, by the first employee, and we will refer that employee as a resource because a resource helps the flow units move from being a unit of input to become a unit of output. And a term referred as activities, it is when a recipe of a sandwich provides you a detailed instruction on how to make the sandwich. It is called activities. So this figure right here will show that this rectangle box as in the resources in the flow diagram, and this arrow to be flow, and then this triangle will be inventory. And then moving on to a flow unit. A flow unit, it is a unit of analysis that we consider in a process analysis. For example, it's like the patients in the hospital or the calls in the call center. And a process flow diagram outlines a directional flow in the process. We refer to the beginning of the flow as the upstream of the process, and the end of the process will refer that as the downstream. So the process flow diagram itself will not tell us anything about the flow rate, but it will capture some useful information and it will be starting point for more quantitative analysis in that moment. So this figure right here, it is the completed process flow diagram. So this green triangle right here is going to be the waiting customer in a Subway restaurant like the previous. In the previous figure, the example will be in a Subway restaurant, and then they're gonna go to the station where they get asked about what type of cheese, the bread, and if they want to get their bread toast or not, and then they'll go on for the toppings and the condiments, and then they will get asked by if they want any additional drinks or food or snacks. And then lastly, the station three will be you pay for the food and then you leave the restaurant. Okay, here is a exercise of how we complete a process flow diagram. So this is this questions. The airport security consists of step one, verifying the ID of boarding passes and boarding passes. Step two, searching the passenger for metal objects using some form of scanner or metal detector. And step three, running the carry-on luggages through an X-ray machine. Uh, so in order to go through the airport securities, you will go through this 1, 2, 3 steps. And at step one, you're just verifying your ID and your boarding passes. Especially step 2 and 3, it will get the line built up because usually when you go through when they search when the security or the person searches for the metal objects on you or the sensitive objects in your luggages, it will they will take up your time. If you do contain any sensitive objects, the machine will go off and then you'll get put to the side and then you'll get asked for if you have anything inside your pockets or your luggages. So that is when step you'll get packed by step 2 and 3. So that's why step 2 and 3 are carried out in parallel. That is when customer go through the metal detector while their luggages is in the X-ray machine. Um, how would we how would we draw a process flow diagram? The answer will be on the right hand side. This is the figure, the diagram of the airport security. So this green triangle right here, it's gonna represent the waiting travelers, the passengers. They're gonna get their ID verified and then check their boarding passes. I don't think they check their boarding passes at the security yet. They're just gonna check the IDs when you trying to go to the gate, and then after that, the person's gonna go through the metal detector, and then while your luggages go through the X-ray machines. So this is the process of the airport security. Okay. Next, what we have here is we're gonna sum it up here. In order to do a process analysis, first, we must fully understand the process flow, and this is why drawing the process flow diagram should always be the first thing in place when you do a process analysis. And it is because it's worth emphasizing that there are many processes process flow happening in any restaurants. For example, that example that I gave, it was the Subway restaurants. And we could have picked a different flow unit than the customer. And lastly, it is also because process flow diagram are flexible, and it is up to whom which aspects of operation you want to study in. And that is it for this section.
Hey everyone, I'm Sierra, and I'm going to be focusing on section 3.2, which is capacity for a one-step process. That will also be our learning objective for this section as well. So, to start off with some key terms, we have processing time. Well, what is processing time? Processing time is the time it takes a resource to complete one flow unit. We also have capacity. Capacity is defined as the maximum number of flow units that can flow through that resource per unit of time. And then we have what is known as process capacity, which is the maximum flow rate a process can provide per unit of time. This determines the maximum supply of the process. The process capacity is the smallest capacity of all resources in the process. So just some general key terms there. So processing time for a one-step process. So let's look at a one customer order. From greeting the customer and ringing them up on the register, there are many activities that take place in completing this order. So all of these steps are referred to as the processing time. The processing time of a resource is how long that particular resource takes to complete one flow unit. So for example, let's say you go to Starbucks and you order your coffee. And let's say that one cashier helps you from the beginning of your transaction to the end of your transaction. So they greet you, they take your order, they start making your coffee, and then they hand it off to you. This would all be considered a one-step process. Another example would be, pretty much anything in business, if there's a single person working that has to complete all of the steps to help the customer. So let's say, for example, you go to a shoe store and there's only one employee there. They would greet you when you walk in. They would help you find the shoes that you'd like, and then they would ring you up at the end. So that would also be another example as well. So then in this slide here, this slide shows a table of the processing time that it takes an employee who makes sandwiches. It takes them 120 seconds per customer processing time. We can assume, though, that the processing times are exactly as shown in this table. Not everybody is going to want every ingredient listed here, so sometimes some of the activities may not be applicable. But this data does capture an average across many customers. So for example, imagine it takes 10 seconds per customer to place the hot peppers on the sandwich. But let's say only 2 out of the 10 customers request peppers. This way, you get 2 seconds per customer on average. So sometimes employees are also faster at making a sandwich, and some are also going to be slower. So you can just assume that all of these steps are just an average. It's not going to always be exact. So as you can see, for example, you greet the customer, it's showing that it takes 4 seconds. And then once you take their order, that takes another 5 seconds. And then once you start getting all of the ingredients listed to make the sandwich, you can see just how long it takes altogether. So in total, it equals 120 seconds. And then this chart also is just another example of processing times in other occupations. So for example, you have cardiac surgery, which can take 4 hours per patient. You have the installation of a rear view mirror in an automotive assembly, which takes about 50 seconds a vehicle. And then you have underwriting a simple small business loan, which can take 40 minutes alone. You have a simple transaction call in a bank's call center, which takes about 5 minutes per transaction. And then you have a primary care encounter, which takes about 15 minutes a patient. So again, this is just another example of all of these different types of processing times that it can take. So here, we want to actually define the capacity of a single resource. So again, the definition of capacity is the maximum number of flow units that can flow through the resource per unit of time. So if we wanted to calculate this and see how long it would take that sandwich artist, we would take 1 over the processing time. So you have 1 over 120 customers a second. And then once you divide that, you do get this very small number, 0.008333 customers a second. It is kind of hard though to imagine that number being a customer. So you can also define it. You can use a more simple way of solving it. So if you take that number that we got and you multiplied it by 60 seconds a minute, you would get 0.5 customers a minute. And then if you multiply by 60 minutes over an hour, you would get 30 customers an hour. So this is a more simple way of seeing it. But again, all of these equations are all of the same. They all mean the same thing. So there's that. And then just basic checking your understanding. So we have some examples here. So let's see. It takes a color printer 10 seconds to print a large poster. What would be the capacity of the printer expressed in posters per hour? So you can see here, you would take that one poster and you would divide it by 10, which would give you a decimal. And if you multiply that by 60 seconds, you would end up with 6 posters a minute. And then if you took that six posters per minute and you multiplied it by 60 minutes, you would end up with 360 posters per hour. And then another example is, let's say a call center has one operator who answers incoming calls. Let's say it takes the operator 6 minutes to answer one call. What would be the capacity of the call center expressed in calls per hour? So it would be kind of similar to the last one that we looked at. So if you divided 1 over 6, you would get a decimal as well. And once you got that decimal of 1.66, you'd go ahead and multiply that by 60 minutes, since there's 60 minutes in an hour. And then you would take that, and you would get a 9.99 number, and then you can just round up to 10. So yeah, that's section 3.2, and I will go ahead and hand off section 3.3 to my group member, Rebecca. Thank you.
Hello class, my name is Rebecca and I will be presenting on chapter 3, section 3. So in this section, we are going to learn how to compute flow rate, utilization, and cycle time. So our learning objective for chapter 3, section 3 is going to be, of course, to determine the flow rate, the utilization, and the cycle process. So in this section, we learn about 3 different equations that we're going to be able to use in order to find, and we're also going to define these 3 terms. So in our first one, we're going to talk about our flow rate. So flow rate, as seen above, is equal to the minimum of demand or process capacity. So a flow rate can either be defined as a capacity constrained or a demand constrained. A capacity constrained is the case in which demand exceeds supply, and the flow rate is equal to process capacity. On the other hand, demand constrained is the case in which process capacity exceeds demand, and thus the flow rate is equal to the demand rate. Sounds a bit confusing, but it's actually very simple. So as you can see in the example below, we are attempting to find the flow rate, right? So we are trying to find it out when the given information is that the demand is 40 customers per hour, while the process capacity is 30 customers per hour. So in this case, our flow rate would be 30 customers per hour. This would be since the demand exceeds supply, the flow rate is equal to process capacity. Pretty simple, right? So what we're doing is we're just taking the minimum from both numbers, of course. So that is how you find the flow rate. Another thing to mention as well is we also have a similar term for flow rate, which is going to be throughput. Very similar, but they both are identical in meaning. So if you ever see flow rate or if you ever see throughput, just know that they mean the same thing. So next, we are moving on to utilization. So what we're going to do is we define utilization. So utilization of a process is the ratio between the flow rate and process capacity. So flow rate, if we want to go into more depth, flow rate is also known as how fast the process is currently operating. And then our process capacity is going to be how fast the process could be operating if there was a sufficient demand. So the utilization is just going to be the flow rate minus that process capacity. So an example I like to use is for a grocery store. For example, say that we have one cashier and they're able to ring up a certain amount of guests per minute. But if there is an insufficient demand met, then that's when process capacity is going to be included. Process capacity will help us get to that sufficient demand in order to improve it, right? Also, one thing to note is that it is very important that utilization can be defined at a level of individual resource as well as a level of an entire process. So on the bottom here, we just have a quick little example or a quick little image of how it is shown. So utilization, of course, is equal to flow rate divided by capacity, which can sometimes be the same thing as seen below. All right. And lastly, we're going to have our cycle time. So our cycle time measures the time between completing 2 consecutive flow units. In this case, it can be defined as 1 over flow rate. So one lifetime example that comes to mind, I'm going to bring back the grocery example. So in a grocery store, suppose that in a specific grocery store, it has an old cash register, and that cash register dings every time that the cash register is to be opened. So our cycle time is going to be the measurement between the 2 sounds of that cash register, right? So that the time it takes to ring up one person to the next person. It also is important that it needs to be consecutive flow units. Awesome, so we're gonna do a quick little example here. So this is an example I have taken from the book. So it's just gonna be, the question is, a primary care doctor has the capacity to see 16 patients per day. The demand rate, however, is only 12 patients per day. So according to this information, we are going to find the flow rate. We are also going to see what is the utilization of the doctor, as well as what is the cycle time, assuming a 10-hour work week. So I'm going to go ahead and let you guys think it over. Think about the last slides we've seen and the equations we've had. Okay. Okay, I'll go ahead and move on now. All right, so in our solution, so first let's go over question A, which is flow rate. So we compute the flow rate as the minimum of demand and process capacity. So it just to reiterate, it shows us that equation once again. So the minimum between the demand and the process capacity, the demand would be 12, since there's only a need for 12 patients, and the process capacity is the amount that the doctor is able to do, which is 16. So the flow rate, very simple, we're just going to take the minimum of the two, so it's going to be 12. So the flow rate in this example is going to be 12 patients per day, right? And next, it's going to be what is the utilization of the doctor. So the utilization, just to reiterate, is the ratio between flow rate and capacity. So our flow rate in this case, which we got at the question above, is going to be 12. And the capacity, right, what the doctor is able to do is going to be 16. So if we take 12 divided by 16, it's going to be 75%. So not 100%, but 75% of the doctor's utilization. So lastly, we are going to have a cycle time. And just like, again, showing you the equation again, the cycle time is equal to 1 over flow rate. So in one day, how many patients is the doctor able to see? But what it's asking us is that over the course of a 10-hour workday, if we only serve 12 patients, what is the cycle time? So one day is 12 patients, which is on that first column right here. And then on the very last one, it can also be expressed as cycle time. And you take one day over 12 patients and times it by 10 hours in one day. So it's going to be 10 hours to serve 12 patients, which, as we see, isn't fully what the doctor is capable of, but this is what it is to meet his demands, which is important. But our cycle time is going to let us know that he can use those 10 hours to serve those 12 patients, right? Awesome. Lastly, I wanted to talk about cycle time versus lead time. So we learned about cycle time in the previous slides. So just to say again, cycle time is the time between completing 2 consecutive flow units. And one term that gets pretty mixed up in there is also lead time. So lead time is the time between when an order is placed and when it is filled. So just a bit different, but I know it could be a bit confusing to hear that. So I'm going to have a quick video here that I'll go ahead and show you guys that kind of explains it more in depth about how to determine whether it would be cycle time or lead time.
The amount of time between when you start a piece of work and when that work has been completed. Whereas lead time is the time it takes for a piece of work to make its way through your entire workflow. For example, the time it takes from ordering something from Amazon to it being delivered to your front door would be the lead time. Still confused? Don't worry, stay with me for a solid understanding. Now, if you're eating at a restaurant, the lead time would be from when someone takes your order to when the food arrives at your table and has been put in front of you. It's when you, the customer, orders something and your mental clock starts ticking. Cycle time begins when the chef begins work on your order, but importantly, not when the order reaches the kitchen. As with lead time, the cycle time ends when the meal is delivered to you, the customer. If you would like any help understanding these metrics, then send me a message in your usual places or leave a comment below. Thanks for watching and have a great day.
Awesome. So that one kind of makes sense with the real-time example. Great. So I'm going to go ahead and pass it over to my teammate, and then they'll be going ahead and discussing Chapter 3, Section 4.
Hi, my name is Aaron, and I'm going to be speaking on how to analyze a multi-step process and locate the bottleneck. First things first, what's a bottleneck? According to the book, a bottleneck is a resource with the lowest capacity in a process. In its most simple form, a bottleneck is a part of the process that causes the system to slow. You can only serve as many customers as your bottleneck allows. This is known as the capacity. It is not possible to get more customers through the process than what we have capacity for at the bottleneck. So, to find the bottleneck, we must calculate the capacity for each process in the process flow. Let's take the example we used earlier about our sandwich workers. In this example, we have 3 employees. The first employee handles all activities leading up to putting cheese on the sandwich. They then pass the process over to the second employee, who handles all activities from placing the veggies to bagging up the sandwich. And the final employee finishes up the transaction by offering the customers any extras such as cookies, chips, value meals, etc., and ringing them up. If we record the average times within each process, this is what we find. The first employee spends an average time of 37 seconds per customer. The second employee spends an average of 46 seconds per customer. And similar to the first, the third employee spends an average of 37 seconds per customer. So just based off of this alone, we can see that the second process takes up the most time, but that doesn't mean it's always the bottleneck. So to be sure, let's calculate the capacity. Our formula for calculating capacity is pretty simple. We take the 1 for a singular customer. So we take 1 for a singular customer and divide that by the processing time of each employee. With that in mind, let's use the formula I just mentioned to find the capacity for each employee and the processes they handle. So let's take the first employee's time spent, 37 seconds per customer, and plug that into the formula. So take the 1 for a singular customer, divide that by 37 seconds spent per customer, and we get 0.027. That means that process 1 has a capacity of serving 0.027 customers per second. You take that and calculate it hourly, and that's a total of 97.3 customers per hour. The same goes for the third employee, considering that they have the same processing times. So again, take the 1, divide that by 37 for 37 seconds per customer, and we get 0.027 customers per second. You multiply that by the amount of seconds in an hour, and we get 97.3 customers per hour on average. So let me mark that real quick. 97.3 customers per hour. Now, we take the second employee's processing time, and use that to calculate their capacity. So doing so, we take the 1 divided by the 46 seconds per customer, and we find 0.022, which means that they help a maximum of 0.022 customers per second, which totals to an average of around 78.3 customers per hour. Sorry, a little bit of a sloppy circle. But what does that mean? As I mentioned earlier, we find the process capacity by identifying the process with the lowest capacity. The process with the lowest capacity is known as the bottleneck. In this example, it is clear that the bottleneck is the second employee within the process flow. The second employee serves substantially less people than the other 2 employees would. Employees 1 and 3 can serve a total of 19 more customers than the second employee. But despite this, the maximum amount of customers that the shop in total can serve is 78.3. The process chain is only as strong as its weakest link. Meaning, although these employees can serve 97.3 customers per hour, because the second employee can only serve 78.3, that's the maximum amount of customers that they can serve. A process can only output as much as the bottleneck allows. It's not possible to process more customers than the capacity within the bottleneck. So let's take the same example, for instance, and let's say that the first and third employee can serve a total of 1,000 customers each within the hour. If the second employee only has a capacity of 78.3, then that's as much as they can produce. Finding the bottleneck is vital in improving the processes to make for a more efficient process flow. It doesn't matter in which part this process takes place, the capacity will remain the same. The image shown here is a visual representation of the sandwich shop's process flow. We have the time it takes for each step recorded. We have how long it takes to greet a customer. We have how long it takes to, for example, put the meat on the sandwich, how long it takes to wrap and bag, how long it takes to ring up on the register. So we have each step broken down and calculated per time and totaled up here at the top. But with the chart, we see a clear peak within the process. That peak, of course, belongs to the second employee. Even looking at it, it kind of visually resembles a bottleneck. See here, the tallest part is the neck. This would be the peak of the bottleneck here. As this is the highest point, we would refer to this as the neck. Next, I will be showing you a short video recapping what we've learned about bottlenecks so far to this point.
Most of us chew a piece of gum now and then. Do you ever think about how it was produced? Well, chewing gum is created on a production line. It's melted, mixed, rolled, scored, conditioned, wrapped, and packaged. What if scoring takes longer than the processes that come before it? Well, much like the narrow top of a wine bottle, this is called a bottleneck. Business process bottlenecks occur when demand outweighs production capacity. Bottlenecks exist at a place where the process is slowed due to an impediment. This could be from out-of-date equipment, inefficient labor, or scarce resources. Maximum capacity is limited to the capacity of the bottleneck. To find and eliminate a bottleneck, we use process analysis. Process analysis looks at the entire business process. Most often, this analysis begins with an identification of all of the business process steps. Then, a flowchart is developed to show these steps. Once we have the steps, we can determine the capacity of each step. Then, when we find the step with the lowest capacity in the process, we have located the bottleneck. Reducing or even eliminating bottlenecks is important to increasing profitability. Boosting efficiency of the business process will improve productivity and expand profitability. After identifying a bottleneck, we can find ways to effectively manage it.
Knowing that we can only produce as much as our bottleneck allows, we must make sure that our bottlenecks are being utilized to their full capacity. In this example, we are being constrained by the bottleneck and not by the demand as previously shown by my group members. Let's calculate using the utilization formula. So taking the same formula shown earlier by my group members, utilization equals the flow rate divided by the capacity. So keeping that in mind, the flow rate in this instance, using the sandwich shop example, would be 78.3 because that's the maximum amount of customers that they can serve. Now let's take the capacity for each process, which in this case for the first process, for the first employee, it'd be 97.3. We get our utilization of 0.804. That would be the same utilization for the third employee as well. But for the second, if you notice, go real quick, the flow rate is equal to the capacity, meaning the utilization is going to be a solid 1 or 100%. So it's being utilized to its full capacity. So keeping those same calculations in mind, the second process has a utilization of 1, which would equal 100%, while the other two have a utilization of 0.804, which is equivalent to around 80% of their utilization. These would be known as non-bottleneck resources. Non-bottleneck resources have a slack capacity, meaning they have utilization levels that are strictly less than 100%, while the bottleneck has a utilization of 100%. In general, a resource might have a utilization level of less than 100% for one of two reasons. A non-bottleneck resource has, by definition, some extra capacity relative to the bottleneck. So, again, we take the max capacity that they can all handle, which would be 78.3 because of the second employee. That's as much as they can handle. That's the max capacity. And if you divide that by 97.3, they're of course going to have some slack because they can never work to their full capacity due to the second employee holding them back, which would make them a non-bottleneck resource. Now, in the case of a demand-constrained process, even the bottleneck would not be working at 100%. If a process is constrained by demand, we might think of demand being the bottleneck, but that's not the case. We will always refer to the resource with the lowest capacity as the bottleneck. So, every process has a bottleneck even if the capacity constraint created by the bottleneck might not be binding. Before handing you off to our next speaker, I'm going to give you a few key points to keep in mind moving forward about this section. So, just to summarize, a bottleneck is a congested area in a process flow that causes a flow to stop or move slower than all other points. So, as you can see here on this graphic, we can handle, and up to this point, there's just this many amount of products being pushed through a process flow. But once it reaches the bottleneck, we can only process 1 to 2 at a time, rather than being able to process all of these at once. So a bottleneck happens when there isn't enough capacity to meet the demand for a product or a service. It's not possible to process more customers in the capacity within the bottleneck. This is why identifying bottlenecks is so important to increasing production efficiency. The best way to eliminate bottlenecks is to increase system capacity by restructuring the process or investing in people and machinery. This will make the process more efficient and have more hands on deck, and maybe more people can tackle that bottleneck to serve more customers at once. Again, this is the end of my section. I'd like to thank you for your time, and I will now be passing you to my partner, and he will introduce the next section. Thank you.
Thank you, Aaron, for teaching us how to find the bottleneck of a multi-step process and how we can determine its capacity. That is going to be very helpful for this next section. So moving on, my name is Andrew, and I will be presenting the first part of the 5th section of Chapter 3. So in this section, we will be satisfying our textbook objective of determining how long it takes to produce a certain quantity. Determining the amount of time it takes for product production is important because it allows businesses to measure the quality of its production. So think about labor, utilization, and efficiency. There are different scenarios that can happen at the start of those processes. So we'll be taking a look at those. So what is lead time? Lead time refers to the amount of time that passes from the start of a process to the end of the process. The reduction of lead time can greatly improve productivity and efficiency while also increasing output and revenue. Here is a video that does a great job at explaining what lead time exactly is.
Hello together, my name is Martin and I'm going to explain you the term lead time on a simple level. So let's start with the example of McDonald's. At McDonald's, we start to measure the lead time the moment the customer places the customer request. So the customer request triggers the production order so that the cook of McDonald's can produce what he has to produce. During that time, we are still counting the lead time. And we stop counting the lead time at that moment when the customer receives his good on the counter. And in an example of McDonald's, the lead time is about 90 seconds. McDonald's is a quite easy example to show the lead time and the effect on the customer, but let's apply this on other industries. Like in the example of McDonald's, the customer orders products. So in industry, we call this the customer demand. At that point in time, we start counting the lead time of that product. So let's see what happens during that lead time. The customer orders triggers internal processes to produce the product. So first we have to bring all the parts to the assembly line. So let's bring the parts to the line. Then the product ordered has to be assembled. So let's assemble the product. Station 1. Station 2. And Station 3. So we stop counting the lead time the moment the customer receives the product. I've seen many examples in which people mix up the term lead time and throughput time. So let me show you the difference of both terms. So first, let's add a buffer of semi-finished goods inside the line and see what happens. Keep in mind, this is no justification of adding buffer to your production line. So once again, once the customer places his order, we start counting the lead time. In this case, the lead time is shorter as we can react quicker on the demand. So we have decoupled the process. But what is the difference of throughput time and lead time? To get that time of throughput time, we can mark a part in the box and measure the time it takes until the part leaves the plant. Keep in mind, as we added a buffer, we have to wait until the market part runs through the buffer. That is the throughput time. In many cases, lead time and throughput time is equal, in some not. Keep this in mind.
So here we have figure 3.6 from our textbook. It is a comparison of the processing times of the subway example used throughout the chapter. Now, what if we want to look at this problem from more of a demand perspective? Anyways, so we ask, how long would it take to produce a certain amount of units, which we'll be referring to as X here. So the formula here is pretty simplistic if you know what your cycle time is, which would be the time to make X units multiplied by the number of units you are inquiring about. So looking at this example here, what if we need to produce 20 sandwiches? How long would that take? For the single employee, this is going to take 120 seconds per customer. So then you multiply this by 20. So we can see that this is going to be 2,400 seconds, which converts to roughly about 40 minutes. Now, if we look at the same scenario, but with 3 employees and a cycle time of 46 seconds per customer per unit, then the time to produce 20 units will be 46 seconds per customer, multiplied by those 20 customers coming through. That will roughly be 920 seconds or about 15.3 minutes. So this diagram is an interesting way of seeing things. Because dividing sandwich assembly process into 3 stages, we were able to produce a lot more product in more or less time. Here are some key terms. So in a worker pace line, workers work at their own pace. If a previous worker finishes before the next, that worker stores the flow unit in inventory. This was demonstrated in our subway example. It wasn't until after the 3rd customer that we were able to complete orders after every 40 seconds. On the other hand, here we have a machine pace line. In a machine pace line, all systems are connected and must work at the same rate. The machine pace line is an alternative to the worker pace line, as steps are connected through a machinery such as a conveyor belt. So all of the steps are completed at a parallel rate regardless of capacity. Here is a process flow diagram for a machine pace line with 3 stations. Notice they are all parallel to each other. This represents that their rates are equal to one another. These lines need to be calculated differently because one involves human beings. Not every person works at the same pace. Machines, however, are perfectly consistent. The time through the empty system is the time it takes the first flow unit to flow through an empty process. Time through the empty system in a machine pace line can be calculated using this formula. It's in machine pace lines that is necessary to calculate this due to synchronization. Now I'm going to hand it off to Tyler.
Hello, my name is Tyler, and I will be finishing up section 5 of chapter 3. So, now the process used in Andrew's subway example assumes that all workers are getting to work immediately. Now, in the real world, this isn't always the case. Therefore, this analysis is not 100% accurate. In a one-step process, the employee is able to start work immediately. But in our example of 3 employees, the third employee doesn't start work until her sandwich reaches her station. So we need to revise our calculations for the time it takes the flow unit to pass the empty process. You have to compute the time until the first customer is served. This is common when stores first open for the day. So, as mentioned earlier, the formulas to find the time to process a unit in an empty system is different for a worker pay system and a machine pay system. So let's start by looking at a machine pay system. In this type of line, the formula to find the time to produce is 1 unit in an empty system is equal to the number of stages times the cycle time. As an example, imagine a toy factory. There are 3 stages and the cycle time for the line is 60 seconds. To find the time to produce 1 unit, all we need to do is multiply 3 times 60 and we get 180 seconds. The reason we can do this is because all the stages in a machine-paced system must spend the same amount of processing time on each flow unit. Refer to the diagram of the machine-paced process. So next, let's look at a worker-paced process. The formula to find the time to produce 1 unit in an empty worker paced system is equal to the sum of all the processing times for each step. So this is pretty simple. This is because each worker works at their own pace, so each stage can have a different processing time. So for example, in a restaurant with 4 stages, the formula to find the time to serve 1 meal would be stage 1, 15 seconds, plus stage 2, 32 seconds, plus stage 3, 24 seconds, and finally stage 4, which is 9 seconds, for a total time of 80 seconds. All right. So the final key term and formula we need to look at is making a quantity of units. So this would be x, using the variable x, starting in an empty system. The fact that the system begins empty is an important one because it changes the formula to find the total of time quite significantly. I will start by showing you the formula and then going more in depth on each part of it. So the total time to produce x units here in an empty system is equal to the time through an empty process plus the number of units minus 1, multiplied by the cycle of the bottleneck step. So the first step of the formula uses a formula we touched on earlier. So that's going to be time through a system through the empty process is the sum of all processing times. So next we have the number of units. So that's going to be x minus 1. We have to subtract 1 from the number of units because the first unit goes through the system is already accounted for by the first part of the equation. So after that, we have 1 fewer units to produce. And the last but most important part of the equation is the cycle time of the bottleneck step. So Aaron showed us that and how to find the bottleneck in our system earlier. So using that knowledge, we can pick the correct cycle time to use for the formula. The reason we must use the cycle time of the slowest step is because that step is the limit in the progress of the whole system. So when you put the whole equation together, you get the time for the first unit to be produced in the empty system, plus the total time for the remaining units to be produced afterwards. So now that we have gone over the formula, we can look at the example below. So in this scenario, we have a business and it needs to serve 20 customers, starting with an empty system. We can see that by looking at the chart of the various stages and their cycle and capacities, but there's only a few pieces of information that we need. So the first is going to be the time through the empty system, which is simply all the processing time summed together. So as we stated before, and that would be the 7 plus 10 plus 10, 7 plus 14 plus 10 plus 7, totaling 38 minutes. The next piece of information is the number of units. So we must serve 20 customers, that's going to be your units. And the last piece of the puzzle is the cycle time of the bottleneck step. We can see by looking at the capacities of each stage that stage 1 is the bottleneck because it has the lowest capacity. So we will use the cycle time of 7 minutes for our equation. Putting it all together, we get 38 plus 19 times 7 for a grand total of 171 minutes to serve 20 customers, starting from an empty system.
To fully summarize and recap Chapter 3, we first learned about the process flow diagram, how to draw it, and the important role it plays by organizing the information a business collects. The topic of process analysis was also discussed, and the impact that it has on a business's success in the long run. In 3.2, we explored the processing time, or the time it takes a resource to complete one flow unit. We also learned about the process capacity, which is the maximum flow rate a process can provide per unit of time, and the formula that is used to calculate it. In Chapter 3.3, we explored the cycle time and its differences from lead time. The formulas are used to compute utilization, flow rate, and cycle time were also discussed. We later learned how to analyze a multi-step process and find the bottleneck. We also explained how to find the bottleneck by locating the smallest capacity in the process. In 3.5, we talked about the lead time and how lowering it could lead to great benefits to a business, such as improved efficiency and increased revenue. We also discussed key differences between machine and worker pace lines and what systems would fit with which one better. I hope that this presentation was eventful and knowledgeable for everyone. Thank you for listening.